Decred employs Blake-256R14, a cryptographic hash function that transforms transaction data into secure, fixed-length identifiers. Blake-256 provides robust protection against preimage, collision, and length extension attacks whilst providing exceptional efficiency. Think of transaction hashing as converting a recipe into a unique fingerprint. No matter how long or complex your transaction data, Blake-256 produces a consistent 256-bit hash that serves as the transaction ID. Let's dive into this hashing process. Step 1. Message padding. Since transaction lengths vary unpredictably, Blake-256 applies padding to create a uniformed size, which are multiples of 512 bits. This involves appending 3 elements to the end of the transaction data. First, a byte marker, displayed here as 80. Then, a series of zeros until reaching the required length, and finally adding a 64-bit representation of the original message size. Step 2. Chunking. Your transaction data gets sliced into precise 512-bit chunks. Imagine cutting a long document into standardized pages of exactly 64 bytes each. Most transactions require multiple blocks, with our example needing 3 blocks to accommodate all the data. As an additional note, sometimes the padding from the previous step forces the creation of an additional block. Our transaction actually fits in under 2 blocks, but padding requirements push it into a 3rd block filled primarily with zeros. Step 3. Initialization. 3 distinct sets of values prepare the hashing algorithm. The initial hash values, H0 to H7, establish a reproducible starting point derived from fractional parts of the first 32 prime numbers' square roots. A mathematical foundation ensuring consistency across identical inputs. Blake constants, C0 to C7, inject additional cryptographic strength by introducing nonlinearity that makes pattern recognition virtually impossible for attackers. The bit counter, T0, T1, meticulously tracks processed data length, ensuring accurate final hash calculation regardless of input size variations. Step 4. The compression engine. The compression function transforms each of our 512-bit blocks through a 14-round process. Picture a sophisticated mixing machine that thoroughly blends every input bit with the current state. Each of our 3 blocks subdivides into 16 4-byte words, M0 to M15, creating the raw material for compression. The algorithm processes blocks sequentially. Block 1 undergoes 14 rounds of transformation, producing an updated state that becomes the starting point for Block 2, and so forth. The compression operates on a 4x4 matrix of initialized values, executing 8 processing functions, G-steps, per round. The first 4 G-steps work vertically through the matrix, while G5 to G8 process diagonally. Each G-step performs calculations that systematically incorporate block words into the function. After 14 rounds, the 4x4 matrix folds into a final state. This state becomes the initial configuration for processing the next block, creating a cascading effect where each block's processing influences all subsequent blocks. Blake-256's strength lies in its mathematical precision. The carefully chosen initial values and constants aren't arbitrary. They're designed to maximize resistance against known attack vectors. The multi-round compression ensures that changing even a single bit in the input creates dramatically different outputs, a property called the avalanche effect. The bit counter's inclusion prevents length extension attacks, where attackers might try to append data to create valid hashes for modified transactions. By embedding the original length into the final calculation, Blake-256 makes such attacks computationally infeasible. This entire process, from blocking through final compression, transforms your transaction data into a unique, unforgeable identifier. The result is a transaction hash that serves as an immutable fingerprint, essential for blockchain verification and consensus.